start. So I'm going to talk a bit about crystal space, some technical stuff, some less technical stuff, giving you some explanation about why we do certain things and how we do certain things, and also a bit about associated projects that go along with crystal space. So first an introduction, and I'll talk a bit about contributors. Portability, this is very important, of course. You have seen this already in the previous talk about FOSDEM. Modularity and extensibility, data structures, debugging, and of course the 3D engine itself, which is one of the most important parts of crystal space. The 3D render, which is the part that renders on screen actually, various other plugins, and then crystal entity layer and the very new Apricot project. So what is a 3D engine? 3D engine is actually something that manages and organizes objects in a 3D world. That's a very generic description, but it actually means making sure that they are represented in an optimal way and that you can easily render them from any kind of viewpoint. It also means an engine also has to manage the surface attributes of all objects, how they look like, the material. Is it wood? Is it stone? What kind of attributes does it have? 3D engine also does visibility determination, which means find out what you should see and what you should render and what is invisible at that point in time. Level of detail. For an object that is very far away, you don't want to render it with all thousands of polygons. That's wasted. And of course, lighting, it's very important too. In addition, there are a few responsibilities that are not really part of 3D engine, but Crystal Space is more than a 3D engine. It's actually a framework. And so we also have support for collision detection, physics, scripting, AI, and sound, among other things. So when I started Crystal Space about 11 years ago, there are a lot of problems that have to be solved. And I have to admit, at that point in time, I didn't solve most of them. So that only came later, while other people joined the team and generally added features for supporting all those problems. For example, one of the big problems for a 3D engine is supporting the latest hardware features of the best NVIDIA or ATI cards, but still work sufficiently well enough on low-end hardware as well, because you don't want to. Many people still have low-end hardware, and you could choose to target only high-end hardware, but we feel that it's better to allow still the low-end as well. Other problems are finding efficient data structures, which is very important in 3D engine because there's really a lot of data that is stored, all the objects, all the data associated with objects, how they are organized. And it has to be stored very efficiently because otherwise you lose speed very quickly. Efficient algorithms are very obviously needed, of course. I will go into more detail about all of these later. One of the major issues is portability. Different hardware, different operating system, different Windows systems. And the classical programming problem that probably everyone who has ever programmed has encountered is debugging. It's, of course, unfortunately, but very needed. So, I already told you Crystal Space is a 3D application framework. It's actually not really specific to games. Just that games are the most used application, but you could also use Crystal Space for other kinds of 3D visualization, architecture, for example, or simulation. It's open source, otherwise I wouldn't be here. It's portable. It runs on Linux, Windows, Macintosh at this moment. In the past, there were even ports for OS2, BIOS, Amiga, but these ports are no longer maintained, so they have been abandoned. It's modular, and I will go into more detail about that because that's very important in Crystal Space. Very extensible, feature-rich, and we support both low and high-end hardware. In addition to Crystal Space, there is also Crystal Entity Layer, which is a separate project. It's also created by me. And it actually adds the notion of game entity to Crystal Space. So Crystal Space doesn't really have to do with games, but Crystal Entity Layer makes it easier to make games. It's optional, you don't have to use it, but it's there, and it can be a help. So there's a short list of a few of the Crystal Space features that we currently have. Portals, Crystal Space is a portal-based engine, also something I will talk about more later. There is a visibility color, which is actually the code that is responsible for finding out which objects are likely visible and which objects are certainly not visible. Particle systems for smoke, fire, you name it. Volumetric fog, landscape engine, very important. Shaders are actually the pieces of code that run on the 3D hardware, and they actually make sure that a polygon or a surface has a certain look. Light maps for lighting, it's one way to do lighting. Stencil shadows is another way to do lighting. Then we also have physics. We didn't make it all ourselves. We use ODE or Bullet, which are two other open source projects. But we have an adapter on top of that, so that an application using Crystal Space can use Bullet or ODE, and it doesn't even have to change its code. It's just a matter of using another plugin. We support sound. We have a virtual file system. We'll talk about that later too. It's one way to solve the problem of the file systems of different operating systems being different. Level of detail, procedural textures, window system based on GUI. It's for in-game menus if you want. You can use that. And a lot more. There are a few screenshots from a few of the projects or test cases. So there are more on the Crystal Space side. But here you see already, for example, at the left side, you can see the landscape engine. There's a particle system in the top right, for example. And here you see this screenshot shows bump mapping on the wall. You see how the wall appears to come out of a bit. So that's done by a shader. And below you see a shader doing toon shading. So you see the outlines of objects. So there are different possibilities. So we started in August 1997, and about 180 people have contributed since then. Most of them very small contributions. There are a few bigger ones. So we have registered our project on OLO, and according to them, we have about 900,000 lines of code. Most of that is C++. It's a bit of Python, a bit of Java, and a bit of shell scripts also. 256 person years, so I didn't do it all alone because I'm not that old yet. And $14 million project cost. I don't know how accurate all this is, of course. It's just what that site told about after analyzing the source code of Crystal Space. So portability. Portability is very important for Crystal Space. We try to target as many operating systems as possible. At this moment, due to lack of maintainers, we only target the major three, so Windows, Linux, and Mac OS. But the code is portable enough so that it's relatively easy to add other ports. So operating systems is one important target. Different CPUs, like Intel or others. Windows systems are also very different. 3D hardware. Sound systems, input devices. So there are a lot of different things that come to a 3D engine, and you have to solve them in a way so that the game developer doesn't have to worry about it. So that's one of the important goals. If you make a game using Crystal Space, you don't have to worry about portability if you do it right. So you shouldn't have to worry about, you just make your code in C++ or in a few other languages. I will go more into that later. And without any modification, except perhaps for the build system to adapt for your compiler, it should run on all three platforms. So operating systems, yes, of course, the obvious problems, the current directory, home directory, finding user preferences, all these things are different on different operating systems. The file system works differently. So you see a few examples there. Also, there's the problem with line endings in text files, which is also different between Windows and Linux and Macintosh. And crystalspace solves that by adding an abstraction layer, virtual file system. And in a crystalspace application, you just use a predefined path for example, game data, some file, and the layer itself makes sure it gets mapped to the right operating system specific path. And virtual file system also supports directly reading into zip archives, so you can just read a file out of zip archive without doing anything special. So CPUs, of course, you have the byte order, little endian versus big endian, how the integers are represented, structure packing and alignment, and different sizes of int, for example, on 64-bit versus 32-bit processors. So all this has to be accounted for. To solve the binary, the packing and the little endian versus big endian, we use as much ASCII format for saving and data as possible. But of course, you can't do that all the time. Images, for example, you have to, they are stored binary. But then you have to be careful. So Windows systems are another big important thing. So there's a lot of difference between X Windows on Linux, for example, and Direct Draw on Windows. It's a completely different API. But again, the game developer shouldn't have to worry about that. He shouldn't have to know. And it's also hard to support all in the same code base. So we actually solve this with different plugins. I will talk more about that later. 3D hardware, many types of 3D cards. Of course, we use OpenGL. So by using OpenGL, we already solve the portability problem partially. But still, even then, it's not enough because OpenGL drivers often have bugs in different combinations. Some cards can't do certain features. So you have to really be careful and see if you use OpenGL this way. On this card it may look good, but on another card it may not be very slow, for example. And there may be another technique that is better suited. So, and there's also the possibility of a software renderer, but these days software renderer is becoming more and more obsolete, so it's a bit of an old plugin now. Sound, again, it's always the same story, different APIs, different sound file formats. Input devices, again, mouse, keyboard, joystick, there are more possibilities. So we have a portable event system so that you can catch events and you don't have to worry how they are handled in the operating system. So that concludes the section about portability. Then another important feature of CrystalSpace is modularity and extensibility. CrystalSpace is a very big project. You saw 900,000 lines of code. But still, to make that manageable, it can't be one single library. That wouldn't work. So basically, the project is split into a lot of modules, more than 100 modules, different plugins. And all these plugins are more or less independent, or at least they only talk to other plugins through specific interfaces. So we call those modules plugins. It's a very important part of CrystalSpace. There are only a few basic libraries, and all the rest are plugins. For example, here are the basic libraries. It's, of course, you need to have support for managing the plugins in the first place, so that has to be in a library. Something has to load the plugins. The APIs for the system-specific tasks, utility classes. Then there's a library with mathematical classes, image manipulation tools, and high-level library for applications to make it easier to use CrystalSpace. So there's a few libraries, normal C++ libraries. And then nearly 95% of code is in some plugin. And the plugin is a representation of some functionality, and we call this a plugin type. So here are a few example types. For example, sound drivers. There's one interface, one API for a sound driver, but then you have multiple plugins all implementing that same interface, so that you can have a sound driver for Linux and one for Windows, for example. Same for image loader plugins. There's one interface for the image loader, and then we have different plugins for all the different formats that we support. A bit like that. It's very easy to write new plugins, even the third party. You don't have to put them in crystalspace. You can also make a crystalspace application and then add your own plugins if you have some very weird image format, for example, and you want to support it, but it's not common enough to be put in crystalspace. Well, then just distribute it with your own application. That's no problem. And every plugin is more or less standalone. So the way to talk, the plugins talk with each other is restricted. So interfaces are one of the most important concepts for implementing a plugin. So it's a bit like Java. In Java, you actually have a keyword interface. The language supports interfaces. It's not present in C++, but we simulate interfaces by just using abstract classes in C++. So, and an interface is a contract. So when you say some plugin implements one or more interfaces, then actually it means that plugin can do these things that are described in those interfaces, if there are no bugs, of course. So, and the set of all interfaces together, that's the crystalspace API. Here's a small example of how an interface could look like in crystalspace. So you basically see it's a structure. It could be a class, but we use struct because the only difference in C++ between struct and class is that the struct, all members below it are public, so you don't have to write public. And we specify the versioning of the interface. That's important, for example, when you upgrade the interface, you add a function or you change a function, you can change the version number so that an application can check if some object implements a certain version of an interface. And then you have the virtual methods. They are pure virtual by the equals 0 at the end. So it means that there is no implementation here. The implementation has to come elsewhere. It comes in the plugins. Here is an overview of the architecture of crystalspace. It's only a small part. There are a lot more plugins, but it shows the most important plugins. So at the bottom, you have the basic libraries. And on top of that, the blue section, that's actually everything that has to do with rendering and operating system window support and events from input devices. So you have the canvas below, which is actually the plugin responsible for opening a window, listening for keyboard, joystick, mouse events, and sending it out to the rest of the application. So you have different implementations, one for X, one for direct draw, and so on. And also for GLX for the OpenGL version, and so on. So there are a lot of implementations there. On top of that, you have a renderer. And the renderer is actually the plugin that interfaces with the 3D hardware or simulates it using a software renderer. And we currently have 3 renderers, OpenGL, which is the default one, the most used one, software renderer, and a null renderer. Null renderer doesn't render anything. It just implements the same API so that you can use crystalspace on the server, for example. So that way you don't need a display. There's also a shader manager. There's a font system. We currently support fixed size fonts or true type. Then on top of all the rendering system, the green bit is actually the engine. It's actually, so the 3D engine itself is one plugin, but to do what it needs to do, it has to use several other plugins. For example, the visibility colors are the plugins responsible for doing the visibility determination. And there are different versions of that. There are render loops, but I will talk more about that later. And the most important part is the set of mesh objects. And a mesh object is geometry. It's actually what you see on screen. And there are also different plugins for mesh objects because there are different ways you want to represent geometry. For example, a landscape is usually represented with a height map. So there is a specific mesh object that knows how to interpret a height map and render it on screen. There are also mesh objects for animated objects, for example, also particle systems. So all are responsible for generating the geometry that is rendered by the renderer, but they do it in a different way, so it's optimized for their specific task. Then on top, the yellow parts is actually everything that has to do with loading. So we use XML a lot. The entire map format is XML. And so you have the map loader, which is on top of everything, and on the right you have image loaders, also with different plugins. And then you have for every mesh object type that you have below, there is also a corresponding loader plugin. And for some mesh objects, there are also multiple plugins, for example, because we also support for some mesh objects binary formats. So you can have multiple loader plugins supporting other formats. And yeah, there's also the XML parser. And then finally, you have the game or the application. At the end of this presentation, I will show you another slide which looks exactly like this one, but which puts this entire block, except for the gray one, in one block called crystal space, and then crystal entity layer sitting on top of that again. So just to put things in perspective. So to get things fast, 3D cards are getting faster and faster, but to actually benefit from that speed, you can't just do naively throw everything at it. You have to do it in a more clever way. So you need good data structures, you need good algorithms to not waste that fast hardware. So here are a few slides about memory management. Allocating and deallocating memory is expensive. I have one very good example of this. A few years ago, one of the big projects using crystal space was PlaneShift, and they had a very big speed problem with loading maps, but only on Windows. On Windows, loading a map was a factor 7 to 8 times slower than on Linux. And after a lot of debugging, we finally found out what the reason was. The XML parser used to allocate lots of objects. It uses a DOM model, which means that every node, every attribute is a separate allocation. And apparently in the Windows version, which was compiled with .NET, if you use, I'm not familiar with .NET, but apparently with the default settings for threaded support, memory allocation is locked to support threads. And that locking was very, very slow. So basically, we rewrote this. So we use pools. We don't allocate as much memory anymore. Instead of allocating one node in a single allocation, we allocate 1,000 nodes and then use them one by one. So we actually got the speed of the Windows version exactly the same as the Linux version. So, and the Linux version sped up a little bit as well, because even on Linux, also memory allocation has some overhead, of course. So we generally avoid linked lists. There are good uses for linked lists, but in general, they add a lot of overhead. One of the overheads is, of course, the memory allocation that you have to do for every node. Of course, you can solve that with pools and other techniques on top of the linked list. But still, in many ways, we use growing arrays. Because Crystal Space is a rather old project now, we don't use the STL arrays. If we would start now, we would use it, but since it's that old, we already created our own utility classes, and they are used throughout the project, so it's a bit of work to change that. But basically, we have the same kind of support as std vector, for example, but in our own classes. And also an important principle that we use a lot in Crystal Space is only do something when you actually need to do it. Don't do it earlier. So, because there are many cases, and I will give some examples of that, when it actually turns out that you don't even need to do what you plan to do. So here's an example, but I will explain that more later. So debugging, it's very important. 90% of the time, I think it's just a rough estimate, but it will not be far away from that. So, and the problem with C++ is that it's a very good language to make bugs in. So you have to do memory allocation and memory management all by yourselves. At this moment, we have a pretty good system for that, but getting it there is also some work. Variables are not automatically initialized, so it's very common to have someone not initialize a variable and have no problem with it, because it happens on this operating system that it happens to be 0 all the time. So, but there are several tools to help debug this, like FileGrind is very useful on Linux, and GDB, of course, just standard C++ debuggers. We also have some debug tools, actually plugins in crystalspace, that help for analyzing, but they are mostly useful for game developers because they can analyze what is on screen and that object isn't rendered. Why isn't it rendered, for example? That kind of things. That's BugPlug. So, and it's a plugin that you can load transparently into any crystalspace application without having to change the code. So, yeah, this is just a way that we also use. We use a lot of asserts in the code to these are only compiled in the code in debug mode, so you get a lot of more checking then. So, one important part of crystalspace is, of course, the 3D engine. So I will go a bit into detail. There are several plugins. You have the core engine, you have the visibility colors, you have the mesh objects and the render loops. I already talked about those earlier. And the engine communicates with the renderer. That's the green part with the, I believe, I forgot the color, with the blue part. So, so crystalspace is a portal engine. That means that to make worlds, you actually use portals to connect different spaces together. And a sector is one basic building block. A sector is just infinite space, and you can fill it with objects, with match objects. And using portals, you can connect different spaces with each other. And the most easy to understand example of a portal is just a doorway between two rooms. Then the two rooms would each be a separate sector. There are also special effects that are possible. You can have a portal that points back to the same place and transforms space so that it becomes a mirror, for example. Portals can move. They are just objects like all the others. So there are different types of mesh objects. I already talked about that earlier. So you have the animated objects, particle system, landscape engine, and so forth. You can also put objects in a hierarchical structure, so that you can have, for example, an actor, which is an animated mesh, having a sword in his hand, for example, which could be a separate object. So, and also lights can be put there. One important concept of crystalspace next to the mesh object is the mesh factory. And the factory is actually the object that contains the geometry, but it's static. What that means is you can have a share in a room, but if you want multiple shares, you only need one share factory and then different mesh objects all using this data from that factory. It's a way to save memory. So here's an example. You have the engine, different mesh factories on the right. And then there are two sectors here. So every sector has a few lights. And then every sector also has a visibility color. So visibility culling is done one sector at a time. And then every sector has a number of objects. And for example, mesh 2 in sector 1 is actually a portal to sector 2. And mesh 3 in sector 2 is actually a portal to sector 1. So here you see an example, a top view of a 3D world. There are 3 sectors here in this case. And the camera is the little eye on the right. And it can actually see into the second sector, the middle sector, through the doorway. But it cannot see the third sector because the second portal is completely out of view. And that's very useful for level performance, because the third room can be a really very complex room. It can contain thousands of objects. But if the camera doesn't see the portal that goes to that room, it has no overhead at all, 0 overhead, because the portal is not even considered. So the objects in that other sector are not even considered for rendering. So it's a great way to speed up your level. Render loops are another concept in the engine as a way to give the game developer more precise control over how to render objects. And we have a very, very general system so that you can actually say, it has to do also with the fact that to render some geometry, some shaders, you need to do multiple passes. For example, you do first to the ambient and diffuse, for example, and then you do bump mapping on top of that. And a render loop controls that by rendering all the objects and having different steps that represent the different passes. So here's an example. It's XML. It's just one of the standard render loops. So you see it has a name. There's two major steps in it. The first step is this one, is actually the one that just does ambient lighting. So it's just a fixed amount of lighting on every surface. And then there's a step, which is also a plugin, that iterates over all lights in that sector. And for every light, it will use another step to add diffuse lighting. So basically what this render loop will do, it will render all objects, and every object will be rendered with as many passes as there are lights hitting that object plus one. So that's how this works. Okay, one of the very important things, even with fast hardware, is still to find out what is visible and what is not, because you don't want to waste time rendering something that is not visible. Of course, if the hardware is fast, you could argue, why not send it all to the hardware? It can handle millions of polygons. Why bother doing the visibility determination if the hardware can handle it? But of course, with the hardware becoming faster, people also expect more, and 1 million polygon object will probably not be big enough anymore. So, and also there are a lot of other things that are associated with objects, like, for example, physics, animation, game logic, and also using the visibility color. If you know some object is not visible, you don't need to animate it. You don't need to calculate the particle positions. You don't need to calculate lighting on it. There are a lot of things that you don't have to do if you know it is not visible. So, but still, because hardware is very fast these days, the visibility culling should be as quick as possible. So, and there are currently 2 and 1 in development, 2 colors in crystalspace. The first one is first fizz, and it's very easy. Just does FOSDEM culling, which means that everything which is outside the view is not visible. Everything which is inside the view is visible. It's very easy. It's very fast, so it is very good if you have, for example, a relatively simple world, and it's no problem to render every object that is in front of you. There's a more complex visibility color, Dynavis, and it tries to find out if some object is hidden by an object that is closer. A KD tree is a 3-dimensional structure to organize data, and it's heavily used by all colors to organize the objects in the world. It's one important of a very important data structure that has to be very fast. So here we also do updates lazy. If an object moves in the KD tree, we don't want to update it immediately. We just put it on a queue and say, if the camera happens to look in this direction, then we will actually move the object up the hierarchy. So here's a quick example. So the entire box represents the world. And first there's a horizon. It's cut in 2 horizontally. So we have a top and a bottom part. Then the bottom part is cut into, again, that way. And then again. So you get every node is cut into 2 halves according to some axis. And objects are distributed that way. So well, the KD tree can be traversed. I will go a bit quicker over these slides. It's a bit technical, and also it's not that important to know it in detail. Just a way to illustrate what an engine all needs to do, the responsibilities, and that it's not that sometimes not that easy. For example, here you see how FOSDEM culling works. So you have the camera at the bottom, and it looks that's the area that it can see. So everything left and right of the red lines is not visible. You can see the rectangles or the nodes of the KD tree. This is, of course, the two-dimensional version, but it works similarly in a 3D version. And you see the dark green areas are areas that are completely out of the FOSDEM. So it doesn't have to render them, and it also doesn't have to check if the objects in those nodes are visible, because it already knows that the container is invisible. Objects that are cut in two by the red lines can contain objects that are visible, so it then has to check the objects. For example, the object on the left, top left is not visible, but the object below that is visible. And of course, you have nodes that are completely inside the FOSDEM, and that's also easy because the objects inside that FOSDEM don't have to be checked either, because if the parent is inside it, then of course the children are too. So Dynavis tries to be a bit smarter than that. It actually tries to calculate if objects hide each other. And to do that, it uses a coverage buffer, which is a bit like a Z buffer for 3D hardware. But I will not go into much detail here because it's really it's really a bit complicated. So, but actually it writes out the objects in a buffer, and it compares the depth with that object with objects that will be rendered later or earlier to see if they are visible. So here you see two polygons, and there's a depth value for every 8 by 8 pixels in this case. There are a lot of optimizations because, of course, this coverage buffer is rather CPU intensive. It actually means you have to transform the geometry from 3D to the screen. And that's actually something that the 3D hardware already does for you. So it's a pity if you have to do it yourselves, again, in software. That way you have to do it twice, once on the hardware and once on the CPU. So there are several ways to minimize that problem. So for example, we calculate outlines of objects, and then we only render the outline in one go instead of every single triangle. That's a lot faster already. We also, when we test if an object is visible, we first test if the bounding rectangle is visible. We're not going to test every pixel or not going to test every polygon even, because if you're going to test if a 100,000 polygon object is visible, that's still going to take a lot of time. So we just test the bounding rectangle, and maybe we will make a mistake, but that's not a big deal. It can be that the object is not visible, but we consider it visible because one part of the rectangle happens to be visible, but there is no geometry in it. But it's better to make that mistake than the opposite mistake. So it's no big problem. We also, writing to the coverage buffer, actually transforming the geometry to the screen is expensive. So we avoid that by writing it, putting it on a queue again. Again, same principle. Don't do work unless you really need to. So, and in this case especially, we found out that very often the work is no longer needed. Also here, history culling. If an object was visible the previous frame, there is a very big chance it will be visible again this frame, because typically from frame to frame, the geometry doesn't change that quickly. So what we do is when we see an object is visible, we say, well, let's make it visible for the next, I don't know, 5 or 6 frames, for example. That way we don't have to test that object again for some time. Also, if we know one point of the object that is certainly visible, then we can, next frame, just test if that point is visible again, and we will only have to test a single point. If it is visible, then we know the object is visible. If not, then maybe we have to do more complicated tests. So there are lots of little optimizations. Well, this is not important. Okay. So Dynavis also supports portals. So when you go through a portal, the view FOSDEM is actually restricted, because when you look through that door, what you can see of the room beyond is actually only a small part. So, and the colors support that notion and know that everything beyond the portal boundary can already be discarded easily. Potentially visible sets, it's a very old system that actually dates from Quake. It actually is a pre-calculated visibility. It's only feasible for if you have static worlds that don't change, and you at every point in space, or at least in nodes, you say this is the list of objects that are visible or not visible at this point in time. We have a PVS plugin, but it's currently not operational, so it needs some work still. Another way to gain speed, besides not rendering what you can't see, is another way to gain speed is level of detail. And an object that's very far away, you only have to render it with very low detail. So, and there are several things that we support. Based on the hardware that you have, you can decide to render it in more detail anyway. If you have speed enough, why not? It may look better, but you can tweak that a bit. So, for example, progressive level of detail is easily shown in this example. It's not my image, it's from Microsoft. So on the right, you have the full detail rabbit, and you have algorithms to collapse that high detail into lower detail, so that in general the shape is preserved, but it just uses less triangles. Imposter level of detail is also very important. It means that you can say you have a very complex tree with lots of leaves, and when it's close, you want to render it in a lot of detail, but when the tree is on a mountain, you don't want to do that. So you could replace it with a lower detail version, or you could let the engine calculate that for you, render that tree once on a texture, and then use that texture instead of the original tree, for example. So we have support for that, but it's not completely functional yet. For portals as well, the contents of a portal, contents of a doorway, if you can pre-render that on a texture, then you can use that texture instead of going through the portal. Static level of detail is very simple, just means like the bunny, different levels, and you can switch between the levels as when you want more or less detail. The disadvantage of that is, of course, that when you switch, you can sometimes see an effect. You see that it suddenly gets more or less detail. So that's the price you have to pay for speed. Landscape is, because it's height map based, has very specific algorithms for level of detail. So here you see an example. On the right, on the left you have a more detailed version, more polygons. On the left there's a lower detail version. And also our landscape engine supports lowering the detail for mountains that are in the distance and more detail for mountains that are close. Materials and shaders, that's another part of the engine that is important. So we support also different plugins, for example CG, RB and fixed shaders we support. And shader is just a program that can run on a 3D card. Because not all cards support shaders very well, we also support the notion of software shaders. That's actually just OpenGL cards that are done on the CPU instead of on the 3D cards. And we support different techniques. For example, you can say a shader for bump mapping. On very good hardware, you might be able to use a fragment shader that does very complex calculations, but does it very quickly and needs only one step, for example, one pass. But maybe that fragment shader doesn't work on lower end hardware, so you can define multiple techniques and you can give them a priority. And crystalspace automatically finds out what hardware supports and will select the highest priority technique that works on your hardware. So that's one way that we can support both high end with high quality and low end with lower quality. Lighting techniques, I will go a bit faster because I'm running out of time. So different ways to do lighting, and light mapping is an important one. I will show that in this example. So on the left you have the geometry. It's a room with some object in it. And it's not lit, which means that you just get the full bright textures. There's no lighting. Everything is the same level of brightness. The light map calculator can calculate light maps. You see them in the second screenshot. So the texture is gone, but you see only the light map. And because there's a purple and a blue light, you can see the different colors. And then finally, it is put together in the engine. And so you see the shadow and the lighting together. Light maps are pre-calculated. So that means that they are not suitable for geometry that changes. Vertex lighting is better. Then you have lighting that can actually change at runtime. And of course, shadows using the 3D hardware, stencil hardware. The advantage, so there is an example, you see the shadows are calculated at runtime here. So if the light moves, the shadows will actually move as well. So the advantage of light maps are that it's pre-calculated, which means that at runtime there is no cost at all. You can have 1,000 lights affecting a single object, and it will render just as fast as the same object with only one light. Of course, it takes a lot longer to pre-calculate, to calculate the lighting in the beginning, but that is typically done by the game developer. And the stencil lighting, on the other hand, has the advantage that it doesn't have to be pre-calculated, and objects can move around and lights can move. But if you have 1,000 lights affecting one object, it will not work. That's simply too much for the hardware. So because it has to calculate it at runtime. So as I said before, we also support collision detection in physics using opcode for collision detection and ODE in physics and bullet for physics. So I will just mention this, but we also have animation, of course, a 3D engine. There are different types of animation. Keyframe animation, where you have different frames, different positions for a kind of object. Skeletal animation, typically used for characters in games. Hierarchical animation, where you can put a sword in the hand of an actor. I already mentioned that, for example. Particle animations, that's obvious. There are also several other animation options. There's a sequence manager that you can have a kind of script that you can say, for example, for 1 second, move that object from there to there. Then after that, it will jump 3 times, and after that, it will rotate a bit. So you can make these kinds of scripts. And of course, texture animation, animated GIFs, movies, animated textures in general. So then below the engine, you have the renderers. So the renderer is actually responsible for sending the data to the OpenGL system or to the software renders. I will not go into a lot of detail here. It's not that spectacular. So the shaders are there. And then crystalspace, well, there are a few hundred plugins. So there are a lot of plugins for console, joystick support, font plugins, scripting plugins. This is very important. I want to mention this a bit more. We actually support Java, Perl, and Python in crystalspace. So you can write a full crystalspace application in these 3 languages, in 4 languages, C++ as well, of course. And it's actually nearly the complete API is exposed. So you can write it in any language that you want of those. XML parsing, sound plugins, movie recorders, sequence managers, reporters, of course the Windows system, virtual file system. Then Crystal Entity Layer, and I will just show you the overview here. So it sits on top of crystalspace, and it adds the notion of game entities, of game concepts. So it does that by defining entities. An entity is a typical object in a game world. It can be something that has a visual representation, but it can also be something that just handles game logic, so it doesn't have to be visual. And you can attach functionality with the property classes. So if you want, for example, a camera, an entity that represents the player, it will typically have a camera, so you attach the camera property class. Then finally, I will conclude by mentioning Apricot. It's a new project started this month, cooperation between Blender and crystalspace, and the plan is to make an open game where everything, all artwork, all sources, everything will be open and published, so you can download it later when it's ready. You can also already pre-order the DVD to help support it, because actually this project is made with 6 people who are actually permanently in Amsterdam working on this right now. So it's one important thing. Here you see it's Apricot projects goes together with the Peach project, which is the open movie from Blender. And these are renders from the open movie. And these characters are also going to be used in the game. So it's a bit of a cartoon game. And this was just an example. It shows Blender integrated with crystalspace, or the opposite way at least. crystalspace integrated with Blender. So it's just one thing that they made in 1 week time in Amsterdam to make it easier to make games using crystalspace and Blender. So there's actually integration between the two. So that's basically it.